Hi, so we're going to quickly work through an MYP problem for the IB here. We're going to take a look at question 1 here, which talks about a frog and a jumping frog. And the reason they're doing this is because one of the applications of quadratic equations, the equations you've just been studying, is how things move through the air. What kind of trajectory, what kind of path does an object, when it leaps through the air or a ball is thrown into the air, what trajectory does it follow? So here in the question you can see a frog leaps from a lily pad. Viewed from the side, its initial position is given by 0, 0. The x-axis is horizontal, y-axis is vertical, and 1 unit represents 1 meter. Draw a graph of its trajectory. Okay, so when you're asked to do this, you need to think of what is the path that the frog will follow when it jumps. And the clue is in this part of your function. So I'll just write the function out nice and large up here. F of x equals 3x over 4 minus x squared over 4. So the minus x squared means you're going to get an upside down parabola. So it's going to look something like this. When the frog jumps up, he's going to go high and then he's going to come down again and he's going to land somewhere. And I'm going to assume, let's just take some colors here. Let's just assume that we want the frog to stay above the surface of some water. He's sitting on a lily pad, apparently, and he's going to stay above the water sitting in his lily pad. But the trajectory, the path he follows, is going to go like that. So that's basically it. Draw a graph of its trajectory, this one down here. Next one, it says, what is the distance that the actual frog goes? And the way to work that out is to think, well, look, he started off on the ground or on the lily pad over here. He leaps into the air and he's going to come down, and the place where he lands is going to be the other zero of the quadratic equation, the other zero of the parabola. Okay, so we're going to take our function and find out what the other zero is. We know what one of them is. It's 0, the point where he took off from. But let's just take a look at that. F of x is equal to 3/4 of 3x over 4, 3/4 of x minus x squared over 4, and we're going to set that equal to 0 to find the 0 points. There's a common denominator there, so we can deal with that very quickly. We now have 3x minus x squared over 4 equals 0. 4 times 0, if we multiply both sides by 0, is going to give us 3x minus x squared is equal to 0. We've got an x term on both sides of the subtraction sign here, so we can factorize that. Take out an x and we're left with 3 minus x inside. That is equal to 0. And with our little rule for how we find zeros, this one must be 0 and this one must come to 0. So our two zeros then are going to be x equal to 0 or x equal to 3. So he starts off at 0, 0 and he ends up at 3, 0. So that's that second part. That's the actual horizontal distance he flies is going to be 3 meters. And we can show that much more neatly using Desmos. So on the other side of this thing, I've got Desmos. Let me just draw that path for you. So there you go. That's his parabola that he takes. The blue water is shaded in. And our calculation means that I've restricted that drawing to between 0 and 3. Okay, so that's parts A and B done. Let's just delete all of that and I'll come back to you with a clear page. Okay, we're back again. The part C, the frog can change its jump by modifying the angle and speed with which it launches. Describe, so we don't need to calculate too much. Describe clearly how its jump would vary if its new trajectory were given by. So we start off with the first one here, y is equal to 2 times x. So if instead of x, the function received 2 times x, what would the trajectory look like? Well, if you stop and think for a minute, okay, if we originally had a 0, a 1, a 2 and a 3 meter frog, and we know that he starts at 0, 0 and he ends at 0, 3, 0, what value would ensure that the function received a 3 if you take that x value and you multiply it by 2? Okay, you should have said 1.5. 1.5 times 2 is equal to 3. So this time what you would see, rather than the frog going the full 3 meters, was that the frog would actually go 1.5 meters before reaching the ground again. We can see that in Desmos. If I open up the Desmos bit here, and you can see there that the frog goes half the distance. And what I can do now is I can actually add back in the axes so that you can see the actual numbers for where the frog is jumping to. So there you go, he lands at 1.5. Originally he got to 3. The height they're going to go to is exactly the same because we haven't actually changed the y output, just the zeros of the equation. Okay. Let's just show the next one. Okay, so it says here now y is equal to 1.2 times the function, but this time we've got 0.7x in there. So the 1.2 is clearly going to multiply, increase the height of the number coming out of our function. This one here, right, if you compare that to the one above, when we multiplied that by a number bigger than 1, 2 or even 3, then the length of the trajectory shortens. It gets less than the original. So this one will do the opposite. It's less than 1. So this is going to cause the trajectory to increase. Imagine if we had put in 3, then what the function would see would be 0.7 of 3, which is 2.1. In other words, it wouldn't have gone far enough to land yet. It wouldn't have been a 0. So we can imagine what's going to happen here is that the function is going to be, it's going to go beyond 3 meters by some distance. Say 3's there and we don't know what that is. But also it's going to be taller than the original function by 1.2, if I could draw that. Okay, so this 1.2 increases the height of the function, the 0.7 increases the length of the function. I'll be able to see that clearly if I open up this one. Here you can see that this one does go further, the line there, and the distance it travels is 4.286, which is 3 divided by 0.7. Okay, take a moment to think about that. Okay, next one then, we're now going to supply a function y is equal to a function of negative x. Okay, if you supply the negative, then really what we're doing is we're flipping the whole thing through the y-axis. So if you've got negative 3, the function returns what would happen if you had 3. Okay, so in this case what you get is the function which is flipped around. Let me just give myself some space there, open up that one, and sure enough it's the mirror image of the original jump of the frog. And this last one here says what would happen, or explain clearly why y equals minus 0.8 times the function of x does not model a trajectory for the frog. Okay, so y equals minus 0.8 of f of x. Well, the reason for that is going to be because when you make that negative, then the output's going to be negative. All of these outputs that you can see here are positive. If you flip one upside down, then what you're actually going to be doing is asking the frog to travel somewhere underneath the water. Instead of being a positive height above the lily pad, it's going to be a negative height below the lily pad. So you can actually draw that one, but that's not going to be anything that the frog could fly through. Frogs don't fly through water. Okay, and we can see the trajectory it would take, which is that one there. And you're not going to get a frog doing a parabola because gravity has got a very, very small effect underneath the water. The actual pulling of the water overcomes gravity. Okay, so I'm just going to turn all those off and show you a little neat feature of Desmos, how we can animate a frog in Desmos. So here, because we've calculated how far he's actually going to go, what I've done is I've got a little frog and he's over there at the moment. He doesn't look very big. Let's just bring him up to full size. Let's just make this a full size screen. Where's the frog? There he is, he's over there. We're going to send him back to 0. Okay. So all we do to animate the frog in Desmos is I've got a function of w. W is just any number I like between 0 and 3. Okay. And then the position of the frog at any one time is just the value w, the distance you put in at the bottom, and then the y coordinate is just the function of w, and the function is this one up here, our original function. So by moving this thing backwards and forwards, we can animate the actual frog's jump, and you can just do that automatically in Desmos. Not difficult to do at all. All I did there was download a little PNG file of a frog, tidied him up a little bit, and here we can actually get him just to keep going the whole time. Poor old frog bouncing backwards and forwards like that. Or we can make it that he just jumps forward all the time. Anyway, that's an amusing end to the video. I hope that you found that useful and that you start to see how you need to apply what you know about quadratic functions to problems like this. See you in the next video.